In this video, we will describe Robert Grubb's personal history as well as the sequence of events that led him to his groundbreaking wide-range chemistry research, including his interests, family background, people he met, and transitions he made. We will also highlight his accomplishments by discussing the importance of the first generation and second generation Grubb's catalyst and the implications these laboratory discoveries had, which span a wide range of commercial applications which we will discuss. Robert H. Grubbs was born in rural Kentucky, February 27, 1942, to a farming family. His father's name was Howard Grubbs, and his mother's name was Fay Grubbs. His academic role models were his mother, who was a teacher, and his grandmother, who prodded her grandchildren to do well, and a practical father who gave him training in mechanics. His interests as a child were building things. Often, he would build objects out of nails and scrap wood. Growing older, he worked at the farm, which allowed him to save up for college, all the while meeting interesting and amazing men and women. His interest in science started in junior high school, fostered by his science teacher, Mr. Baumgartner. Grubbs started at University of Florida under the agricultural chemistry degree, which combined his interest in both the sciences and agriculture. Organic chemistry had left a big impression on him in how simple observations with basic chemical reactions is the power of organic chemistry, in which he claimed that is more fun than building houses. He then studied on to Columbia University in New York City and became the first student of and worked under Ron Breslow. In 1969, he finished his fellowship with Coleman, Michigan State University, MSU. After 9 years at MSU, he started to work with olefin metathesis and in various areas of catalysis, and then was offered a position at Caltech in 1978 and moved to California in the same year. Robert H. Grubbs is alive today, married, and has 3 children. He was awarded the Nobel Prize for his achievement and his work on the Grubbs catalyst in 2005. Throughout his career, Robert Grubbs achieved and received many awards, but we will only be able to describe some of them. Grubbs was awarded the ACS National Award in Organometallic Chemistry in 1988. The American Chemical Society recognized Grubbs' most recent advancement at the time having a major impact on research in organometallic chemistry by providing an understanding of the preparation, reactions, properties, and structure of organometallic substances. Another of his awards was the Benjamin Franklin Medal in Chemistry in the year 2000 by the Franklin Institute. During this time, his work began to greatly advance and expand the field of olefin metathesis, a unique carbon-to-carbon bond-making process that has enormously added to the chemist's capabilities at making a broad range of drugs and other useful complex molecules, improved rubbers, and plastics for laboratory and commercial applications. Again, the largest achievement that Grubbs was able to attain was the Nobel Prize in Chemistry in 2005.
Robert Grubbs did a lot of work in olefin metathesis, for which he received his Nobel Prize. So, the purpose of olefin metathesis is to rearrange carbon-carbon double bonds. Now, the nice thing about this is you can have a lot of different rearrangements. If it rearranges with the same carbons again, you just end up with your reactants. But you have the possibility of it rearranging with another carbon-carbon double bond, for which you can see the product on the right. Now, this has many different applications in organic synthesis, petroleum industry, polymer chemistry. Basically, anytime you want to kind of change the groups on different carbon-carbon double bonds. Here we can see the synthesis for the first generation Grubbs catalyst. Before the Grubbs catalyst, in order to do an olefin metathesis, it wasn't that green. You needed a lot of reagents. But ever since the Grubbs catalyst, all you need is a little bit of the catalyst, your solvent, and then you can just run your reaction. Now, the last product of here is the first generation Grubbs catalyst, and we can see this metal complex with 2 chlorines on it, 2 PCY3 groups. But the important thing about this complex is that metal ruthenium and that carbon double bond. And that's what's going to take place in the mechanism for olefin metathesis. Here we can see the second generation Grubbs catalyst, which was invented sometime after the first generation. So the problem was that PCY3 group was too electron donating. They needed something that was going to be more electron withdrawing. And putting this kind of nitrogen ring complex with these two benzene rings. That was a more electron withdrawing group, and what this allowed to do, it allowed the complex to be more electron withdrawing, and that increased the reactivity of the complex by quite a lot. I believe it was 10 to the second or 10 to the third fold. And there was other benefits using the second generation Grubbs catalyst. For example, it was a lot easier to work with in the lab. It was less reactive to moisture in the air. And this second generation Grubbs catalyst largely replaced the first generation Grubbs catalyst in use. Now here we can see a little bit of the differences between the first and second generation Grubbs catalyst, but it looks like the main difference between these two, besides the reactivity, is just that the second generation Grubbs catalyst undergoes thermodynamic control, while the first generation undergoes kinetic control. Now for the mechanism of olefin metathesis. So here we start with this double bond and this R1 group. Now, we're going to have the metal double bond come in, and we're going to form this metal ring complex that's going to have the R1 group attached to it. The main proof of this mechanism comes from the fact that we have this four-member ring complex, and that can be seen in other experiments in which the products tell you that this must be the mechanism. You're going to have this ring complex condense, and that's going to give you this double bond with other stuff on it. And you're going to have the metal now attached to the double bond with the R1 complex on. Now this can undergo another opening and form another ring complex with this R2 that's double bonded to something. You're going to have this metal R1, R2 ring complex. Now that can condense, that can kick off the product that you want, which is this R1, R2 double bonded, and that's going to regenerate your Grubbs catalyst with the metal double bonded to something. We see that in the first generation Grubbs catalyst with this pH group attached to a carbon, which is double bonded to the Ru metal center of the Grubbs catalyst.
Grubbs catalyst has a lot of application, mainly in carbon-carbon double bond forming or breaking reactions. Some include cross-metathesis, ring closing chemistry, making polymers, and ring opening chemistry as well. Some of the large applications don't come from the Grubbs catalyst itself, but from the knowledge of how and why it works, then making deviations from the catalyst to work more specifically. The Grubbs catalyst mechanism is used in ring closing these reagents in order to more efficiently produce this osteoporosis drug. Variations of this catalyst, as well as the general mechanism, is used to make hepatitis C drug as well. The Grubbs catalyst also has application in green chemistry. It's green because the starting materials are renewable and simple structures. The processing has few or no byproducts, little or no solvents, and low energy input. The products replace polluting materials and replace petroleum-based material. The Grubbs catalyst and metathesis mechanism is also used to combine two rings to have a ring complex inside of a ring complex. This in itself will open up new fields of study and application when more research is done. Previously, in the synthesis of large natural products were made using many steps and large number of starting materials to combine and create the final product. However, using a variant of the Grubbs catalyst and the metathesis mechanism, many large and natural products can be created in significantly fewer steps. Another application of the cross-metathesis knowledge is gained from the Grubbs catalyst is to synthesize pheromones to use as pesticides. They are able to do this from the functionality learned from the Grubbs catalyst as well as its green chemistry. Finally, the Grubbs catalyst is used in seed oils, mainly corn and soybean, as they can be modified using the olefin metathesis to be converted to value-added functional molecules.